Hello, in this topic we'll talk about the Hartley oscillator, which is part of tuned oscillator. At the end of this topic, you should be able to describe the operation of Hartley oscillator and draw the waveform associated with it, analyze the Hartley oscillator circuit and derive the transfer function of the feedback network, determine the frequency of oscillation of Hartley oscillator, and lastly, you should know how to design Hartley oscillator. Hartley oscillator is introduced by Ralph Hartley in 1915. This type of oscillator, if you look over here, consists of amplifier and a feedback circuit. The feedback circuit is a positive feedback and the amplifier can be any type of amplifier. In this example, it is a bipolar junction transistor. This is common emitter amplifier. The output is taken into the feedback and it is fed back to the amplifier. This is also a Hartley oscillator, but this is inductor coupled. The tank circuit or the feedback network consists of two inductor and one capacitor. Hartley is opposite of Colpitts, whereby you have two inductors but one capacitor. Okay, and in this example, it is another type of amplifier. It uses RFC, radio frequency choke, and the output is coupled through the inductor. Okay. Analysis of Hartley oscillator in this topic, we will use op-amp to depict the operation of Hartley oscillator. Okay, the feedback network is the bottom part. It is a positive feedback, consists of two inductors, L2 and L1. L2 is connected to the output while L1 is connected to the input of your amplifier. There is only one capacitor. The output is a sinusoidal waveform if it satisfies the Barkhausen criteria. And in this example, your amplifier over here is inverting amplifier. Thus, the feedback network must introduce another 180 phase shift. In order to analyze the feedback network, first, if you look over here, this is the part or the branch that is connected the feedback network to the amplifier. Usually the RA is chosen such that it will be much larger compared to the inductance. So RA usually is chosen to be 10 times XL1, and with that the current entering the amplifier through the RA can be considered 0. So we can ignore this and we left with only the two inductors and one capacitor. This will simplify the analysis of the feedback network. Okay, looking here is the total impedance. We have to find this total impedance for this particular circuit. The feedback network can be redrawn. The capacitor and inductor is in series, so it is shown clearly in series. This two is parallel with L2. So your total impedance looking at this particular node will be L2 parallel with C and L in series. Okay, so we can write that the total impedance Z is equals to JXL2 for this inductor. It is parallel with these two in series, which is JXL1 minus JXC. So meaning that JXL2 is multiplied with in bracket JXL1 minus JXC divided by JXL2 plus JXL1 minus JXC. Okay, simplify this equation. Open the parenthesis. JXL2 multiplied with JXL1 will give you minus XL1 XL2 because J squared is minus 1. JXL2 multiplied with minus JXC will give you plus XL2 XC. And at the denominator, you have J. This is also J minus J. So we can rewrite that J in bracket XL1 plus XL2 minus XC. Okay. The frequency of oscillation is obtained by setting the imaginary part to 0. The imaginary part is the denominator over here. So equate XL1 plus XL2 minus XC to 0. And from this, you can get that XL1 plus XL2 is equals to XC. Substitute XL, which is the reactance of the first inductor, with omega L1. Similarly for XL2, it is omega L2. And for the capacitor, the reactance XC is equals to 1 over omega C. So from this, you have omega squared is equals to 1 over, I bring over L1 and L2 to the bottom. So it is 1 over C in bracket L1 plus L2. So the frequency of oscillation from here is omega naught, which is 1 over square root of C in bracket L1 plus L2. And L1 plus L2 is called L equivalent. This is in radian per second, and in hertz, the F0 is equals to 1 over 2 pi square root of CL equivalent, where L equivalent is actually the total of your inductor, L1 plus L2. We have redrawn the feedback circuit just now. L2 is parallel with C and L1. So we want to find VF in terms of VO. Your VF is just the voltage across L1, but from this node to ground, across C and L1 is your VO. So using a voltage divider, your VF is equals to VO multiplied with JXL1 divided by JXL1 minus JXC, which is these two impedances. Okay, simplify this, bring over VO to the bottom. So your beta, which is defined as VF over VO, equals to XL1, the reactance of the first inductor, divided by XL1 minus XC. And we have determined at the frequency of oscillation, the XC is equals to XL1 plus XL2. So substitute XC with this, and your beta will equals to XL1, similar to this, but substitute XC with XL1 plus XL2. Simplify this, XL1 minus XL1 cancel out, so you left with XL1 over XL2. There is a minus sign, so meaning that your beta is equals to minus omega L1 over omega L2, and this negative indicates the phase shift for the feedback network. Since the feedback network has a negative sign, it introduces a 180 phase shift. So that's why for your amplifier, it is a inverting amplifier. Your RA going to the input terminal, the negative side of your op-amp, and this is your VO. And for this type of amplifier, the gain will be minus RF over RA. Again, there is a negative sign, so meaning that your amplifier will give a 180 phase shift. And in order to satisfy the Barkhausen criteria, beta multiplied with A must equals to 1. So your A, I just take the magnitude, is RF over RA, and just now the beta is the ratio of L1 over L2, equate it to 1. So the ratio of RF over RA is equals to L2 over L1. So meaning that in order to design a Hartley oscillator, you must make sure the ratio of RF over RA is equals to L2 over L1. And please remember that L2 is the one that connected to the output, while the first inductor, L1, is connected to the input. So in order to design a Hartley oscillator, you must make sure your RF over RA is equals to L2 over L1. You must make sure you cannot interchange the position of L2 and L1. Otherwise, you'll get a wrong answer, because the ratio of L2 over L1 will equals to the ratio of RF over RA. Again, the amplifier is inverting amplifier, so it is minus RF over RA. Your beta is the ratio of minus L1 over L2, negative 180 by the inverting amplifier, another 180. So the total phase loop around the circuit will be 360 degrees. So in order to design this amplifier, you must make sure RF over RA equals to L2 over L1. And the frequency of oscillation is 1 over 2 pi square root of CL equivalent. And if you design the circuit correctly, you'll get the sinusoidal waveform at the output section. And for the frequency of oscillation, the L equivalent is the summation of the two inductors, L1 plus L2. Thank you.